In this lecture, we will prove this lemma 3, which was used in the proof of Mordell's theorem. So in this lemma, we talk about doubling the point. So doubling the point increases height. So this logarithmic height or small height of 2p is greater or equal to 4 times height of the point minus some constant kappa, which depends upon ABC, and this ABC was nothing but the coefficients in the cubic curve. So say this point P is given as x comma y. So this is this point. So if you double it using the doubling formula, so say you get this psi and eta. So this psi is given as a ratio of two polynomials, and you can check this, that this is given by the doubling formula. So if you check this doubling formula, you will find out that the degree of the numerator, the degree of this polynomial is 4, and degree of denominator, that is this polynomial, which is psi, is 3. So degree of phi is 4 and psi is 3. So to prove this result, we will actually end up proving this portion here. So height of 2p is height of this first coordinate psi. So this becomes height of psi, and then this is greater than d times, so d is our degree of this phi, so this will become 4 times height of our point p. So p is m over n, so height of p, and some kappa 1 we will determine. So you can see this height of psi, which is 2p, so this 2p is precisely height of psi, so this is greater or equal to 4 times hp minus kappa 1. So now let us understand what is this result which we want to prove. So we want to show that there are, say, two polynomials, phi and psi, and their coefficients are integers, and their greatest common divisor is 1, so that is they're relatively prime to each other. They have no common factors actually in complex case also, not only in integers but in complex case also they do not have any common factors. So this is 1. Then you set d as the maximum of degree of phi and degree of psi. So from here, for these x's, we plug in rational numbers like m by n. So what we want to do is we want to find an integer r which does not depend upon these rational numbers, and greatest common divisor of n to the power of d, this polynomial, first polynomial phi, instead of x we are putting m by n, then n to the power of d again. So this n here is same as the n in the denominator, and this d here is the maximum degree, and in the proof it will be clear why we are multiplying by nd. And again here instead of x you have m by n, so you take its greatest common divisor, which we denote by gamma. This gamma divides r. So this is the first result we want to prove, a, and then b we want to prove. From a, b will follow. So b will be, there are two constants kappa 1 and kappa 2 which depend upon our polynomials, this phi and psi, such that for all rational numbers m by n which are not the roots of our polynomials phi and psi, so what we are doing is we are omitting a finite number of points. So finite number of points are omitted which are corresponding to the roots. But as we have seen before, this is not going to make much of a difference. So for all rational numbers m by n we will have these two inequalities. So this first inequality proves this result right here, and second inequality we will just show, because once we have done the hard work, this is also easy to show. So as we said before, we are dealing with heights, and taking out finite number of points does not impact, because for a finite number of points we can actually compute the height like this. So you can compute for those points and then appropriately adjust this kappa 1 so as to make this inequality hold. So for a finite number of points, height does not really matter because you can actually compute it, so you know the bounds. Yeah, so let us now start by proving this part A and then part B. So we have to show that this gamma, which is greatest common divisor of these two terms, this divides some integer r, and this r is independent of all rational numbers m by n we put inside. So to start with, we have these two polynomials. You set degree of phi as d and degree of psi as e. E is less than or equal to d because you're setting d as the maximum of the degree of these two. And you can interchange psi these two if you want to, because we are taking the greatest common divisor here, so it's not going to make much of an impact. So you set this capital phi as nd times this small phi m by n. So we are multiplying this by nd because instead of x, when you plug in m by n, you will have some denominators, and since the maximum degree is d, if you multiply by nd, you can cancel out everything. So for the first term you had md by nd cancels out, and then you can see, so you can notice now all terms have degree d. Similarly, for this capital psi mn, you again multiply by n times d, but this might have degree less than d, so there might be some terms remaining like this. So you have b0 me and e minus 1 and so on. Again, if you add up the degrees, it will add up to d. So here and here we have cleared the denominators, nothing much. So this and this will just be integers now. So here if you plugged in m by n, you could get a rational number, but we have multiplied by this and this so as to get rid of the denominator. So now this phi and psi are relatively prime because we have already said that they have no common factors in complex numbers. So obviously in a smaller field also they are not going to have any common factors. So you have some polynomial fx and gx in rationals, so that this is equal to 1. Now we want to do the same trick for f and g. So first, we don't want any denominators in the coefficients of f and g, and then when we plug in m by n, we want to get rid of the denominators for f and g as well. So first, to clear the denominators for f and g, you multiply by some big number a which contains all the factors of the denominators, so it cancels out everything. So we have to multiply with big number a on both sides so as to get rid of the coefficients. Second, we want to get rid of the denominators which come in once we plug in m by n for x. So x we are going to plug in as m by n, and now we want to get rid of this denominator, exactly like we got it here by multiplying n to the power of d. So again you set d as maximum of degree of f, degree of g, same technique like this. And now you multiply throughout by a n capital D plus small d. So we are multiplying by a to get rid of the coefficients, n to the power of capital D to again get rid of this denominators, and then this small d to make this phi and psi into capital phi and capital psi, just to get this. So this is this we get by multiplying this by 1. Now again we are carrying fx and phi x like this. So fx and phi x are here, a is here, and this is nd, and this is small d. Again similarly here g and psi are here, and then we are just using this term a is right here and small d here, capital D is here. So obviously once you multiply this with this, you get capital psi right here, nd times psi, and this nd times phi will get capital phi. So multiplying these two gives you capital phi. So again notice that this entire thing is nothing but capital phi. This entire thing is nothing but capital psi. So now we set gamma, we define gamma as the greatest common divisor of this phi and psi, capital. So gamma is the greatest common divisor. So gamma is going to divide this side because it divides this capital phi. It also divides capital psi, so it ends up dividing this side. And notice that these are integers. So we need this to be integers to be able to say that gamma is the greatest common divisor here, and these two are integers, only then it can divide this. So we needed them to become integers. So gamma divides this. So we have shown that gamma divides a n d plus d. We have to show that gamma divides r, where r does not depend upon the rational number we plug in, which is m divided by n. But right now we have this n here, so we want to get rid of this n. So what we will do is we will show that gamma actually divides this other number, which is some coefficient a0. This coefficient a0 is coming directly from here. This md is also coming from here, and then we decrease this by 1, and then we keep on decreasing it. So that is our trick. So now to show this holds, we have to show this holds. We actually focus on this equation right here, and you multiply both sides of this equation by a n d plus d minus 1. So we are multiplying this right here. So now you multiply it here also. So a0 md you keep as such, and then here you have this a, and on the other side you have n d plus d minus 1. Now you go to the second term, you keep a 1 md minus 1 as such, this as such, but this n times n plus d, n to the power of capital D plus small d minus 1, this minus 1 and this 1 here will cancel out, so you just get n d plus d, and this a is as such. So again you keep on doing like this. Now we have already shown that gamma divides a n d plus d. So gamma divides a n d plus d. So now you see that gamma also divides this capital phi. So gamma divides this, and gamma divides this, which we have shown here. Now this term is everywhere. So this term is in this term, a n d plus d. It is also here, a n d plus 2d minus 1. It is also here. Only here this term is not there, a n d plus d, because we have d plus d minus 1. So gamma is dividing this phi here, and it is dividing all the other terms except this one. So since it divides both sides, so it has to divide this term. So gamma divides a0 md n d plus d minus 1. But when we take these rational numbers m by n, we take them in the lowest form. So m and n are relatively prime. So this m does not really matter here, because there is no m here. So if gamma divides this, it divides this entire term, and you can forget about m. So gamma divides a0 n d plus d minus 1. Now we are going to use the same trick here, repeat the argument, and show that gamma divides a0 square n plus d, this n to the power of d plus d minus 2. So from here minus 1 we have gone minus 2. So again for the same argument, now we multiply both sides. Again we are using this first equation. We are multiplying both sides now by a0 n to the power of this capital D plus small d minus 2. So multiply this to this side and then to this side. So a0 md you keep as such, but now you're going to multiply by a0, so you get a0 square md, as you can see, and everything remains as such. So again you multiply here, you get a0 a1, so a0 a1 md minus 1 remains as such, and then you have this n to the power of 1 multiplied by n to the power of d plus d minus 2, so that becomes d plus d minus 1, and so on. Now here we have shown that gamma divides this term right here. So and we said that we are going to skip m because m was relatively prime. So we are saying that gamma divides a0 n d plus d minus 1. So gamma divides this portion here, but it also divides phi because it is by definition greatest common divisor here. So gamma divides this and it divides this, but this term, as you can see, occurs here, and it occurs in every term after this. So gamma divides this term and every term which occurs here. So it is dividing everything, so it has to divide this first term also. So that is the thing. So gamma divides this first term, which we are writing here, a0 square md n d plus d minus 2. Again this m and n are relatively prime to each other, so we forget m. We say gamma divides a0 square n d plus d minus 2, and that's what we wanted to show right here. So we keep following this procedure, and at the end we end up showing that gamma divides a0 d plus d, and now you can see this, you can say is r, because there is an integer r which gamma divides, and this r does not depend upon m by n. So notice no m and n come in here, although this a0 comes from the coefficient of this polynomial. So this a0 is the coefficient of this polynomial. So this already occurs, it is coefficient of this polynomial. So it does not depend upon x because it's a coefficient, so it does not depend upon the rational number you plug in. So that was our part 1. So we have been able to find this r here, and gamma divides this r, which does not depend upon the rational number m by n. So now we want to prove part b of the lemma, that there are constants kappa 1, kappa 2 which depend upon our polynomials, such that for all rational numbers except the roots, except a finite number of points which are just the roots of this polynomial m by n, this inequality holds. So this thing we are going to call as psi. So this inequality will hold. So let us see this in detail. So you set psi as this term, phi over psi is psi, this psi here. So if you multiply both this by n to the power of d and n to the power of d, we, by our definition, we get capital phi here and capital psi here. So this is psi, say. Okay, so this is it, and we have this gamma here, which is our greatest common divisor of, now this term we know just by this multiplication here is our capital phi, and this term is our capital psi. So gamma divides r. So if gamma divides r, this r is actually giving us, if you cancel this r out, because this r might be a common factor, if you cancel this out, you're going to decrease the height. So the height is just maximum of our first term, which is capital phi and capital psi, because that is the height of psi. So height of this is nothing but maximum of absolute value of this or absolute value of this, just these two terms. But now we can cancel this r out because there is some division, because these might have a greatest common divisor gamma which divides r here. So we can take 1 by r here, so that will decrease the height, because if you're going to cancel some factors out, if you cancel something out from the fraction, then the integer in the numerator and integer in the denominator decreases, so these integers become less. So this height of psi is greater or equal to 1 by r max of this. Now we have this our inequality, that max of, say, ab, this is greater or equal to half a plus b. And that's what we write here. So from here we come here, and this 1 by r we said because of this relation. Now we can divide both sides by height of m by n d. Now again, what is this height of a fraction like this? So this is a fraction again consisting of numerator and denominator, so this is max of and that's what we plug in here. So this, so now we are dividing both sides by this height, so this we are just copying as such. So now we divide both numerator and denominator by nd. So you divide numerator also by this and denominator also by this. So you get this in the denominator, because this nd over this nd becomes 1, and numerator you start getting these terms, small phi m by n and psi m by n. Again, because you know that this capital phi is actually a function of m and n, you divide by nd, you get this small phi. Again, you divide this capital psi by nd, you get this small psi. And that's what we get here. So this entire thing we will denote by p m by n, like a polynomial. So this polynomial we will show, so we still have to show that this is bounded below by some constant. So we will show that this is actually greater or equal to some constant c1. So for now, assume that this is greater or equal to some constant c1. So you can now put, instead of this polynomial here, you can put a constant c1 and greater or equal to sign. So instead of this, we have put c1, 2r remains as such. This thing we now carry over to this side here. So now you just take log. So you take log of this, you get here take log of this, you get right here dh m by n. Set kappa 1 as log of 2r over c1, so log of this. So now you put minus kappa 1 here because obviously plus kappa 1 will give you c1 over 2r. Log of c1 over 2r is plus kappa 1, so you have to have minus kappa 1 so as to invert this, and that's it. So this is what we wanted to show right here, this inequality. So height of psi is greater or equal to d times height of m over n minus kappa 1. So now we have to only thing show is that p m by n is greater or equal to c1, and then we will talk about this inequality. So this p m by n, which we said was this thing we are going to rewrite here like this. So instead of m by n, we write t. So this is it. So as t goes to infinity, so p of t will approach the value of a0. That's precisely because d is the maximum degree of phi and degree of psi, and we are saying degree of phi is d. So this phi has the maximum degree, and therefore the coefficient value is a0. Just in case that this also has e is also equal to d, then you will also get b0. So you will get either absolute value of a0 or absolute value of a0 plus b0 as the limit, and you can see both these are greater than 0. So this is as absolute value of t is going to infinity. If you're working on a bounded interval, then you see that this is continuous here, continuous here, and continuous here, and all these values are positive. So the function p of t is also continuous and it is positive. So it is continuous, it is positive, that is greater than 0, and it is continuous on a bounded set, so it will obtain its maxima and minima. So by Bolzano-Weierstrass theorem. So therefore you can just set some minima as equal to c1, and that's precisely what we did. We set the minima as greater or equal to c1, and we used that right here. So now we show this inequality. This is very easy to show. Again, recall that this height was nothing but equal to maximum of absolute value of this and then this. So this we are going to use. So first focus on this result right here. So we will take this right here, take absolute values on both sides, absolute value here, absolute value here. So now we take absolute value of each individual term, so you get a less than equal to sign right here. And now you know that m to the d, this is less than equal to hmd, so that's what we put corresponding to the first term. For the second term, both md minus 1 will be less than equal to, so this will be less than equal to say h d minus 1, n will be less than equal to h, so product of these two will be less than equal to h to the d. So just looking here, so instead of d you're putting in 1 or d minus 1, so you get again d, because the sum of every term here is d, so again nd is less than h by m n d, so this is what you get. So you take the common things here, do the same thing for this psi. So absolute value of psi now is equal to absolute value of this, now less than equal to for individual terms. So again now you still get h m by n d, because you can see that you add up the degrees here, you get degree d, you add up degrees here, you get degree d, because you're multiplying by this n to the power of d right here. So again, because of this degree d, you can again have this, because you can keep on changing degree to get this heights of different degrees, and you multiply them, you will still get this d here. So again you take this, take the coefficient here. So height of psi, which is this, basically psi, we can set it up as capital phi over capital psi, or this, because you can just multiply numerator and denominator by nd to get this term. So height of psi is maximum of either this or this. So we are copy this entire thing right here, copy this entire thing right here, this height, you copy right here. Now take log. Log of this is this, log of this is this, THM over N, and log max of this is kappa 2, and that proves this second inequality. So we are done with lemma 3 of Mordell's proof.